Hello, everyone, and welcome to today's webinar. Thank you all for joining us today. My name is Maike Diekmann. I'm the Technical Support Manager at Thorlabs Germany, and I will be moderating this webinar. Today's webinar is the third installment in our light characterization series. Today's topic is beam shape profiling, so we will learn about different methods to characterize a beam, the importance of the M-square factor for beam quality, and how to measure it. I'm very happy to welcome back Manfred Gonnert as our speaker. Manfred has a background in electrical engineering and has been working for Thorlabs and its predecessor for 30 years now, starting in production before moving into R&D. Today, he's the head of our light detection and analysis group, which designs and develops our light analysis product line, including power meters, beam profilers, polarimeters, and many more. He will give a 45-minute presentation, followed by a Q&A session. You're welcome to submit any questions throughout the presentation or during the Q&A session. To do so, just click on the Q&A button on the top right of the screen. Now with that, I will hand off the talk to Manfred.
Maike, many thanks for your introduction. I would also like to extend a warm welcome to our audience to this webinar on beam characterization. Today, we will talk about the geometrical properties of laser beams as well when looking at the cross-section and the propagation direction. We will start with an overview about laser measurement in general, continue with some basics about beam geometry, and move over to understand beam shape and quality and methods to measure those. To warm up, let's jump into what kind of measurements can be done around a laser beam. First obvious is the optical power or the pulse energy measurement. This can be done with an optical power or energy meter and an appropriate calibrated sensor. You can find a lot of basics and practical hints in the recorded power meter webinar on the Thorlabs website. Not only the power level is from interest, there are many applications where the exact pulse form or the interpretation of a modulated signal needs to be investigated. Here, a suitable detector and amplifier is usually used, and an oscilloscope or a fast data acquisition card help to understand what's going on. In order to understand the subject area of light detection with very small signals with low noise results, I also want to point to the corresponding recorded webinar from this summer. The wavelengths of the emitted light can be measured with spectrometers, wave meters, or spectrum analyzers. For many applications, it is important to know the polarization state of light. Thorlabs offers various instruments about polarization measurements and components to control or manipulate the polarization. The last issue of this webinar series will be spot on this in late November. Finally, we want to get to the geometrical properties of a laser beam. For the cross-section of a laser beam profilers are used to measure the beam diameter and beam intensity distribution. In order to be able to make a statement about the beam quality and thus about the quality of the laser source, a beam profiler in combination with an M-square measurement set is required, which can scan and evaluate the beam in the direction of propagation. And here we see what we want to talk about today. First, let's understand what cross-section and the propagation of a laser beam is about. The distribution of light confined with a laser resonator is described by spatial patterns called transverse modes. Transverse modes are eigenmodes of the laser resonator, and an ideal laser emits a Gaussian beam, the so-called TEM00 mode beam, TEM hereby stands for transversely excited mode. That 00 is the lowest order mode. It has the lowest threshold, smallest beam waist and divergence, and contains no nodes in the output beam transverse intensity distribution. Higher modes are less efficient and occur especially with high laser powers, what affects larger beam radii and higher divergence. Real laser beams are a combination of the basic TEM00 mode and the higher modes. The examples here show on the left side rectangular and on the right side cylindrical transverse mode patterns, both starting from the 00. As already mentioned, Gaussian beams can be focused to the smallest beam width, and an ideal round Gaussian beam propagates with the fundamental TEM00 mode. In most cases, especially with diode lasers, so-called edge emitters, there will be an elliptical beam. That means it propagates with different divergence angles between the fast and the slow axis. In addition, it is possible to form other important beam shapes from Gaussian beams. First, to mention the top hat shape that can be formed with microlens arrays or diffractive optical elements. The cross-section is basically a cut-off bell curve and used when it comes to the necessity of a homogeneous illumination, for example, of biological probes. Next one, a donut-shaped beam emits the 0-1 transverse mode. It can be shaped with a lens and vortex diffractive optical element combination. Applications here can be found in optical communication, optical trapping, or laser detection and ranging. Compared to a Gaussian beam, a bezel beam is not subject to any self-diffraction. It can be created from a Gaussian beam with an exicon. Applications for bezel-shaped beams are used in microscopy or in optical tweezers. The TEM2, the first number here, stands for the number of the spatial rings. That can also be more, so then it would be a TEM3, for example. And the second number, the 0, stands for the fundamental mode again. So why is it important to know the beam diameter, or even more the intensity of the cross-section? On one hand, you may want to know if your beam overfills your detector. On the other, when it comes to higher intensity, you may want to go sure that your optical component or sensor can be exposed to the laser beam safely. The beam diameter can be measured on any cross-section of the laser beam along the propagation path in different directions. You usually look at the X and the Y axis cross-section. And there are three commonly used definitions that, used correctly, should give the same result for a Gaussian beam. The most straightforward here is the full width at half maximum, what is a common term for defining any pulse width. The beam center here is taken at the maximum, and the beam diameter is measured between the 2 points when the intensity has dropped by 50% or -3 dB. With a Gaussian beam, it means that approximately 76% of the beam intensity is within the calculated width. However, to characterize a laser beam, there have been established certified definitions for the beam width that differ from the method above. First to name is the clip value that defines the beam width at 13.5, or exactly when it dropped to a value at 1 per E square of the maximum power. This definition is recommended for Gaussian beams by the American Standard for the Safe Use of Lasers and the Federal Aviation Administration. The method is usually used with mechanical beam profilers. When the diameter has been determined with the full width at half maximum method, the obtained value must be multiplied with the factor of 1.7 to get the official 1 per E square diameter. So especially with camera beam profilers that can see the full cross section, the ISO 11146 recommended second moment width or D4 sigma method was established. It uses the full region of interest, ROE, and takes 4 times the standard deviation of the intensity along major and minor axes. By calculating the second moment of the beam profile, it is possible to characterize all kinds of higher mode beams as well. However, it is very important to compensate against background light and not saturate the sensor at the maxima. When we look now at the beam propagation of a Gaussian beam, there are the following important parameters. The beam waist is the radius at the position with the smallest cross section. Further, the Rayleigh length is the position where the waist has increased by the factor of 1.41, or exactly by the square root of 2. The divergence half angle is a measure of the spatial spread of a laser beam in the far field. The far field is defined beyond 4 times the Rayleigh length. Below this, we speak about near field. And at every cross section, the beam shape is Gaussian. At the beam waist, the intensity of the beam is the highest. Moving towards the Rayleigh length, the Gaussian shape doesn't change, but the intensity profile flattens since the beam waist is broader. In that region, the wavefront changes from a linear wavefront to a radial wavefront. And here, when we are moving further towards the far field, the profile is still Gaussian, but it comes more to an even intensity distribution. For many applications, it is desirable to achieve as small as possible spot size that bundles all the laser power or energy. Therefore, it is good to have a definition that quantifies the focus ability of a laser beam. When focusing a laser beam, the width cannot go completely to 0, what would mean that the intensity in this spot would be infinite. Like an hourglass, there will always remain a certain waist that limits the intensity in the so-called focal spot. And then this minimum waist is dependent from the wavelength, the convergence angle, and the most from the beam intensity profile. And here again, for an ideal Gaussian beam, the W0 waist is the smallest that can be achieved, and this is given by the beam parameter product constant. That is the product of the beam waist radius and the divergence half angle measured in the far field. The beam parameter product of an ideal Gaussian beam is only dependent from the laser wavelength, and it has the unit millimeters times millirad. In general, a beam can be focused the smaller, the lower the wavelength, and the steeper the convergence angle. Or in other words, the smaller the focal length of the focusing lens used. And for real laser beams, the beam parameter product constant must be multiplied with a factor called m squared. M squared is hereby the ratio between the beam parameter product of a given beam, the real beam, and the beam parameter product of the ideal Gaussian beam of the same wavelength. M squared quantifies the beam similarity to a perfect single mode times 0, 0 Gaussian beam whose M squared is 1. Lower beam quality beams or all real rays have higher bandwidth parameter products and therefore higher M squared parameters. So now that we know the basics about beam shape and waist, we will look how these parameters can be measured. We are starting with measuring the shape with the knife edge method. And this easiest way to measure the beam diameter is to scan the beam by an edge that is perpendicular moved through the laser beam and measuring the passing optical power with a photodiode. Of course, the photodiode must be large enough to fit the full beam. First, we have to measure the full power level. Then we move the edge across the beam, and by knowing the exact positions of the edge at 84% and 16% of the intensity, it is easily possible to calculate the beam width. In order to explain why the 83.9 and exactly 16.1 percentage values are the right integral and error functions from the measured intensity values must be solved, which I would like to save here. Important is to know that it is sufficient to know the full intensity and the edge positions where the signal drops to 84% and to 16%. If you derive the obtained curve, you get a Gaussian intensity distribution. Projecting the beam radius, half beam diameter, you get the half diameter at 60% of the 1 per square root e of the intensity curve. If you apply double the value, you get the desired 1 per e square beam diameter at 13.5% intensity. So the manually moving the slit with exact measurement of the power and the position with a micrometer is a bit elaborate. To automate the method, it is possible to use an optical chopper instead. The laser beam is measured with an amplified photodetector that is connected to an oscilloscope, where you can use the direct measurement function of rise and fall time. When knowing the 10 to 90% rise time, the chopper speed, and the correction factor of 1.56 to compensate for the 84-16% values, This gives a nice method to get the 1 per e square beam width. You can find all details to this experiment on the Thorlabs website in the Insights section. The advantage of the knife edge method is given by the simple setup and the uncomplicated algorithm to determine the beam diameter. Disadvantage here is that this method works only for Gaussian and especially for round Gaussian beams. And yeah, to overcome the disadvantage, we will get to a more sophisticated scanning slit method, where the knife edge or chopper blade is replaced by slits in some micrometer slit width region. With that, we are coming to the scanning slit beam profilers. A scanning slit beam profiler consists of a drum with 2 or more orthogonal oriented slits. And this drum rotates around a photodetector, whereby the slits are crossing the beam path. The processed and integrated signal of the photodiode in relation to the drum, and therefore the slit position, is used to measure the beam intensity profile and calculate the 1 by e square beam diameter. With this method, both X and Y profiles can be acquired with each revolution of the drum simultaneously. I will start an animation. The slit moves along the Y direction and the blue profile is recorded. And you have seen the next slit moving along the X axis. And here you can see the recorded red X profile. And to achieve reliable results, the beam diameter must be a lot larger than the slit width. And for calculating the beam parameters, the circumference of the drum, the slit width, and the speed of the drum need to be known. The calculation of the beam profile is performed by integrating the measured intensities for both X and Y direction. And once the beam profile is taken, the beam clip value will be calculated and displayed. The advantages for the slit beam profiler are that they can deal with fairly high power levels because the majority of the light is blocked from the photodiode by the small slits. And to cover the wavelength range from UV to the mid-IR, there are several models available. Measuring very small beams is also possible by the built-in knife edge mode. This is similar to this knife edge method we shown before. And in this case, the beam must be smaller than the slit. Otherwise, it won't work. The main disadvantage is that the profile is only scanned in 2 orthogonal cross-sections. Therefore, it is not possible to get a full intensity map of the beam. Further, for higher mode beams, some of the features may be missed. And to overcome this issue, in combination with the slit beam profiler, it is possible to adjust the angle position of the slit by turning this internal drum and hit so the main axis of the beam distribution. When it comes to measure a real 2-dimensional intensity profile and display nice 3-dimensional profiles, A camera that sees the full cross-section must be used. And with that, we will come to the next topic, the camera, beam camera or camera beam profilers. A beam camera consists of a modified camera chip with a sufficient large field of view and pixel size. The modification is necessary to avoid unwanted interferences caused by the protection glass of the sensor chip. There are further coatings that allow the visualization of UV light. The camera detects and displays the intensity profile of the incoming beam, independent of the beam shape. And due to the high sensitivity of the sensor chip, appropriate optical filtering is necessary to prevent from saturation or, in worst case, damage of the sensor. So I'm now releasing the laser beam, and we can see it passing through the ND filter and hitting the sensor chip, followed by calculating and displaying a full two-dimensional intensity profile. In this case, you see a donut-shaped profile. To calculate the intensity profile, the measured current from each pixel is used and processed to a three-dimensional coordinate system. The beam diameter is calculated according to the ISO 11146 recommendation with the D4 sigma method. It is very important to measure the background that gets subtracted from the following beam measurement. In order to list the advantages of the camera beam profilers, the uncomplicated mechanical structure should be mentioned first, as it does not contain any moving parts. Second, the camera can measure any beam profile, inclusive higher transverse modes or patterns generated by optical elements, or even more than one laser beam. Main disadvantage is the limitation of the operating wavelengths to UV to NIR due to the silicon sensor chip. There are cameras with indium gallium arsenide sensors on the market, but usually the cost is far higher at a worse resolution. In general, the pixel size limits the smallest measurable beam size. As a rule of thumb, the beam should be larger than some 4 times the pixel size to measure the diameter. So, for example, the pixel size of the camera is 3.5 microns, and therefore the smallest measurable beam will be some 15 micrometers. Last point to mention is the higher computing power required. On the other hand, with the camera with the camera itself, the FPGA processing, and on the other hand, for evaluating the data on the computer, because you have much more data that need to be handled. And here I would like to point out the latest generation of Thorlabs camera beam profilers, which will replace the current BC100 series. The new Thorlabs BC12207 series beam profilers are built with a passively cooled monochrome CMOS camera chip with a resolution of 5 megapixels. A 12 megapixel version with double imaging area is under development as well. The pixel intensity is measured with a 12-bit analog to digital converter. To be able to cover a high dynamic range, a removable 6-position filter wheel containing filters up to 60 dB attenuation comes with the beam profiler. The camera itself is also capable to hold a 1-inch neutral density filter. There are various mounting and alignment options as 6 or 1/4-inch threads for TR or pillar posts, and easy centered access to the aperture with 30mm cage bores or a centered SL1 thread. The BC12207 is also designed to fitting the Msquare Measurement kits. As already mentioned, a sufficient attenuation of the laser beam is necessary before it can be exposed to the beam profiler. The easiest way to attenuate a laser beam is the use of a neutral density, as it is built in the filter wheel of the camera beam profiler. The attenuation happens while the beam passes through the filter. There are absorptive versions for the visible and IR range, or reflective for the UV to IR range. Both have advantages and disadvantages. Also, anti-reflection coatings can be added for various wavelength ranges. And D-filters in general are limited to a certain power density that will destroy the coating or melt the filter glass. Therefore, there is a very effective way to attenuate higher power laser beams built upon 2 wedged glass blocks that reflect a portions of the beam. The shown Prism attenuator offers here an attenuation of 30 dB and is suited for power levels from below milliwatts up to 200 watt in the uncoated or up to 50 watt with anti-reflection coating. The advantage of this filtering method is that it doesn't influence the beam's polarization or shape. The attenuators can also be cascaded to get to a safe power level that is detectable with the beam profiler. As next, I would like to lose a few words to the measurement of pulsed lasers, since most material processing lasers are falling under this category. For laser measurement with high repetition rate, the measurement equipment works in a quasi-continuous wave operation. You don't have to care about anything. But when coming to lower repetition rates, the pulses always will interfere with the drum rotation of a slit beam profiler or with the frame rate of a camera beam profiler. Therefore, a sufficient averaging needs to be set to get a smooth profile. And with the camera beam profilers, the exposure rate can additionally get increased, and hereby you need to take care about the sensor saturation again. In general, as for any laser measurement device, please stay within the maximum rated power or power density levels to not destroy the instrumentation. In the next slide, I want to give a short demonstration on the provided Thorlabs beam software. So the following video will show the measurement of a more or less Gaussian beam with a camera beam profiler. There are various possibilities to visualize the beam as the X or Y profile, 2D projections, or 3D profile. Further, all kinds of beam parameters, beam diameter, ellipticity calculation results are shown in a table. Now I start a live measurement. We select arrow E area. We can set a binning. As the next, we can select what results to be shown. Here we're starting with the 4 sigma values, also the 1 per e square values. You can zoom into this 3D profile and also select the quality of this profile. And further adjust the region of interest, either with automatic modes or manually. You can either do it in this overview picture or directly in the X or Y profiles. And here I want to show another nice feature that shows and evaluates the beam pointing stability. So the beam profiler follows the maximum intensity spot and plots it over the sensor area. Okay. And now to summarize the beam profiling device section, here is an overview between the both beam profiler types. On the left side, the slit beam profiler, on the right side, the camera beam profiler. While the slit beam profiler works best with Gaussian beams, the camera can be used for any kind of beam, even with complex mode patterns. The spectral range of the slit profiler goes from 200 nanometers up to 2700 nanometers, while the camera is limited due to the silicon sensor to the 1100 nanometer. Beam diameter range can be from 2.5 microns up to 9 millimeter with the slit, and from 15 microns to 7 millimeters with the camera beam profiler. The calculation method for the slit beam profiler is the 1 per e square, and for the camera, the 4 sigma method. And power levels can range from nanowatts to 10 watt without further attenuation for the slit beam profiler, and from femtowatts to 1 watt with the filter attenuation, or extended up to 50 watts with the prism attenuator. And both methods work for pulsed lasers as well. And now in the last chapter, we will have a closer look what happens along the beam path while measuring the M-square. To measure the M-square of a collimated beam, it is necessary to focus it and scan the area before, close to, and after the focal point. Therefore, the beam profiler sits on a translation stage and moves along the beam path. The beam profiler hereby takes the X and Y diameters at several points and plots them into a graph. By connecting the points and interpolating the curve, you come to the beam waist position and compared this to an ideal Gaussian beam with the same beam parameters, with the same divergence and the same wavelengths. And now knowing the beam that has been measured and the ideal beam, the M-square can easily be calculated by taking the ratio of both. The setup here shown is very space consuming. Further, the heavy beam profiler needs to be moved, what especially with the mechanical slit version may cause additional noise to the measurement. Therefore, the Thorlabs M-square measurement system looks a bit different. The beam profiler sits steadily mounted on the exit port of the device, an appropriate focusing lens on the entrance. Within the light-tight box, the beam is reflected through the box by two tilted mirrors, and these mirrors sit on a translation stage and can shift the focus through the detector of the beam profiler. At every position, the diameter measurement points are taken. Here we see the measurement of the first diameter. The stage moves and the beam profiler again records the beam diameters. For simplicity, I show it only for one axis here. Next position along the beam path. Now another one behind the focal point. And finally, after at least 5 points around the focus and another 5 points beyond the Rayleigh length, before and after, the beam waist can be determined and compared to the ideal Gaussian beam waist under the same divergence. And finally, the M-square can be calculated. Now that we have seen the mechanical approach, let's have a look at the software. In the first example, I will show a M-square measurement with a camera beam profiler. The incoming laser beam must be collimated with a focusing lens. And yeah, we start the animation. We select the M-square measurement button, make some settings to use the 4 sigma method, and start the measurement. The beam will be scanned along the z-axis and the beam width point is taken all 10 millimeters. Here you can see moving through the focal point. This was the first measurement. We see that there haven't been enough points within the Rayleigh length for the ISO calculations. Therefore, the beam is scanned in a second way closer at the Rayleigh length. And now we can get, with this additional points, we get the ISO valid calculation of the M-square values for both X and Y direction. We get displayed all this. On the right side, you have the X and Y values for the M-square, Rayleigh length, and so on. And all these parameters also recalculated for the original incoming beam. There is a second thing you can do with this M-square measurement system, and this example shows a divergence measurement, also performed with a camera beam profiler. The incoming beam must be collimated. The focusing lens, the set here, needs to be removed from the entrance of the M-square setup. So the measurement is started by selecting the divergence measurement button, and by the record button, and the beam again will be scanned along the z-axis, and a certain number of beam width points are taken in the pre-configured distance, in this case all 4 millimeters. And when finished, the divergence angle for both x and y direction and the additional statistics get displayed. So on the Thorlabs website, Msquare Measurement system can conveniently configure to your needs. You can choose between all kinds of available slit or camera beam profilers. Further, you have to select the desired wavelength operating range for the best anti-reflection coating of the tilted mirrors. Both beam profiler and stage are operated with the same software. Once you get through this configurator, you will get your part number and, of course, price and availability. So with that, we are coming to the end of this webinar. I'm taking the chance to point to the further webinars in the light characterization series. In November, the last issue of the light detection webinar will be about polarization measurement. All past webinars can be found on the Thorlabs website. Thank you for watching and listening. It is now time to address a few questions. Therefore, I'm giving back to Maike.
Thank you very much for the presentation. It was very interesting. As you said, we're now doing the Q&A session. We received quite a lot of questions during the presentation, so just in case we're not getting through them all, feel free to reach out to us, to your local tech support as well, but we'll try to answer as many of them as we can. Okay, let's get started. So I saw a couple of questions that were about the minimal focal spot that you can detect. So the question came up for both camera and scanning slit beam profilers. So is there a preferred method for characterizing small focused spot sizes? What can you do if you have a 9 micron beam waist in the focused? And another person asked if you can detect 10 microns with a camera. So a lot of questions about what the smallest size we can see is.
Okay, thanks, Mike. All very interesting. Yeah, as mentioned, there are limitations of the real spot size. On the other hand, since we are scanning along the beam path, we don't need to exactly hit the focal point. So as long as points aside the focal point can be measured or can be sufficiently resoluted, the calculation even goes a bit beyond the minimum measurable spot size. I hope this helps.
Yes, and I think the actual values that we specify were given at a point after the questions were posted here. So yeah, hopefully it was already answered. Then let's see. So there's a question if our camera has an auto exposure feature to prevent sensor saturation.
Yes, simply yes.
And also if there's any processing difference between our old and our new camera beam profilers, such as the distance between two peaks.
Yeah, there is a slight difference since the new camera has much more pixels, much higher resolution, and therefore you can add binning features to put together more pixels. Therefore, the measurement can be accelerated. There is a minor ambient light correction. and you have various possibilities to limit the region of interest. So in general, the operation is a bit more convenient and helps to find the right images.
Okay, thank you. Another question about the camera beam profiler. Can it be used for high-speed pulsed lasers? And the customer suggests between 1 kilohertz and 10 kilohertz repetition rate.
Yeah, this shouldn't be a problem at all, since the frame rate of the camera is far below this kilohertz.
So you would not be resolving the pulses in that case, right? Because they also asked that.
Right. Yeah.
So you can measure, but you're not resolving the pulses.
Okay. Right.
Okay. Let me see what else. So there's a question, I guess, that came during the video, noticing that the beam size changed based on where in the aperture beam the scanning slit beam profiler was hit, and if that's something unusual or if that's a normal feature.
No, it's not normal. It might be a specialty of this used laser during the video. So if you don't center the beam, you will get the same beam size as if you center it.
Mm-hmm. And then there's a few more questions about the scanning slits. So one customer wants to measure the divergence of a beam, which should be 290 microrads, and wants to know if it's possible with our Msquare system.
We have to do some math here, but usually this is in a region that should work.
Feel free to reach out to us with your question again if we should do the math. Okay. And also that the focal length of the lens in the Msquare system is 250 millimeters. Is it possible to increase the focal length in order to increase the accuracy of the device?
So the most important thing here is that you have your focus in a spot where you can go a bit before the Rayleigh length and a bit after the Rayleigh length. So it really depends on the laser that needs to be measured. I cannot answer this from spot. We would have to come back to this question.
Okay. There's also just a confirmation about the knife edge method. This only works for Gaussian beams, correct?
That's correct, yeah. So the right beam diameter 1 by e square can only be calculated with a Gaussian beam, with a knife edge. You will get a diameter, but it's not the right one for other beams.
Okay, so there's a lot of very different questions, so I'll just get to another one. On the comparison page with the camera beam profiler and the scanning slit beam profiler, it was written that the camera uses the 4 sigma method and the scanning slit the 1 over e square. The customer would like to know if the camera could be set up in the software to also use the 1 over e square method.
Yes, this is possible.
Okay, great. Okay, I think that's about, there's a couple of new ones. Some customers who want to have the PDF slides, we will reach out to send you something there. There's also a few questions about the BC12207, when it will be available. I guess it's coming soon. In case you need a solution for a camera beam profiler urgently, just feel free to reach out. We will see what we can do in that case.
That's the
Okay.
best answer you could give.
No, it's nearly ready, so we
Yeah,
can
yeah.
probably
Really.
find a solution if you reach out to us. Okay. Are there any other questions for the time being? I hope I didn't miss anything, but I think we covered it. In case anyone has any further questions, as I said at the beginning, feel free to reach out to us anytime. You can reach your local tech support, or you can reach us at europe@thorlabs.com. Be sure to come back for our 4th and final installment in the series, which is in December, about polarization measurements, and also to check out our other webinars on our website. So thanks again, everyone, for attending. Thank you again to Manfred and to your entire team for the great presentation. And we hope to see everyone soon. Bye-bye.